Okay. So yeah, so instead of observing some passive dynamics of some particular physical system, then we can actually make Hamiltonians, which is the crucial ingredient in terms of controlling a quantum state. And we can sort of control it in the way that we like. So we can apply unitary operations that we can design. And basically, quantum computers would be made of certain things, and it really depends upon, the research group and, well, these days, commercial company that are trying to make quantum computers. And, we're really at this kind of very early stage in quantum computer development because nobody really knows what a quantum computer really still looks like. So some people consider this like a similar age to when people were trying to make airplanes for the first time. And so, we know roughly, what airplanes should look like these days. But at the beginning, people were trying all kinds of, funny ways to make airplanes. And in the end, there's a particular design that worked. And similarly, in quantum computers, people are trying all kinds of things. So these are the kind of systems that people are trying to make quantum computers out of. So things like atoms, using the electronic orbital states of atoms, light itself. So you can use photons as and consider that a quantum system, and use light to create various quantum states. Solid materials, so you can maybe design new crystals with different properties. These types of micro and nanomechanical resonators. I don't think actually people are trying to make quantum computers with this particular system, but people are doing experiments to make observe certain types of quantum states. And the interest in these systems is a little bit more that what's the limits of when quantum mechanics breaks down. So normally we associate quantum states with small stuff. Now these things are small, but actually not so small. It's not like a single atom level. This is much bigger than a single atom level. This is like 10 microns. 10 microns is like 1/100th of a millimeter. I think it's not quite visible with the naked eye. A single hair might be a fraction of a millimeter. So this is much bigger than a hair. Maybe like 10 of these kind of things here might be, when I say here, so things like, this might be the width of a human hair, for example, roughly speaking. Diamonds is another one. So defects in diamonds, people try to use that as quantum information storage sites, or qubits, and talked a bit about that. Superconductors is another. This is more of a macroscopic quantum state where it's like the wave function is involving a lot of different particles, and this is what gives it its very special properties. And bosons and condensate, this is what I'm working on actually, and this is like a atom version of a superconductor, similar types of physics. Okay, so I think this is where we got up to. So what we're going to start today is actually talking a little bit more abstractly about quantum computers, and we're going to talk about really, the kind of the common element of quantum computers. So we're not going to really worry about the sort of the real kind of physical system, like is it an atom or a photon or anything like that, because actually when you come down to it at this sort of fundamental level, it kind of looks all the same. So it's just particular energy levels or particular states, and then they form your quantum state eventually on your quantum computer. So basically, a quantum computer is you might think of it's like the ultimate controllable quantum system. So it's you can control basically every aspect of it. And what I mean by sort of every aspect is that the technology is still developing. So there are certain systems that you can have sort of partial control of the quantum state. So maybe you can only perform certain types of operations, and it doesn't allow you to make a completely general quantum state. So if I had a bunch of qubits, maybe I wouldn't be able to access certain types of states, but in a quantum computer, it's assumed that you can. And so so that we're going to talk about that a little bit more, basically how we can achieve that. And basically in a quantum computer, what you have always is a bunch of qubits, as we've got here. So we're going to deal with like many of these qubits. And we can think of each one of these as just, this two-level system. And basically in a quantum computer, if you've got, let's say n, so this big N, this many qubits, then because when you make a state out of these many particles, the state can be in any combination of any of these states. So for example, in this 8-qubit system, you can have any number of states or any state which is like combination of all these, say 256 different combinations, because each one of these ones could be 0 or 1, and basically any of those, so any like 0, 1 combination of these would give a unique distinguishable type of state. Okay, so they're distinguishable because you can definitely tell it's a different type of state. So for example, here we've got the state 0, 0, 0, 0, 0, 0, 0, 0, so all the states in the down level, all the way up to 1, 1, 1, 1, where all the states are 1, and basically anything in between. So when we represent these qubits, you can represent them in a number of ways. So the first way is simplest to just write down literally the representation of these states. So just, what is each one of these qubits? What is the state they're in? So this is like the literal state that each one of these qubits can be in. But this can be a little bit long. So, for 8 qubits, we've already got, this thing which looks kind of long. So sometimes what you can write is that you can treat this as a binary number, and then say, okay, well, let's just convert that binary number into a decimal number. Okay, then you get something a little bit more compact because, we don't have this long string. We can write it instead of this just as a 3-digit number, right? So then you could equally write it as these states on the left or the right. So, so basically then what you'd have as an arbitrary quantum state is, a state that looks like this. So you have basically any combination of all the different distinguishable states that you can have. So there are going to be 2 to the power of n quantum states for big N number of qubits. And because each one of those combinations can have a different coefficient, so then the wave function, the coefficient of the wave function we can write like this. And so it's basically some, we call it some variable A, and then, it has as many subscripts as the labels that we have here. So each one of these n's, so n1 is just a sum, this is a sum over 0 to 1. And so because you'd have big N of these nested sums, and each one of them runs over 2 nest, n of these nested loops basically gives 2 to the power of n possible combinations. So in the binary representation, we can write the state something like this, a general state of the quantum computer in that way. Or we could also write it in this sort of decimal representation, where instead of running over all these different sums here, we just run over one sum, where we just go, between 0 and, well, in the previous page's example, it would be like 255. Okay, so 0 to 255, and that's just the decimal version of this number here. And then in that case, we just have like one label, M, which just runs over all those cases, and we could also call it A. Okay, so that's basically how you write a generalized state. It's basically just a generalization of like what we've already learned when you have more than one particle. So this is just the many particle version of it, and you can basically just see that this is a kind of an extension of that. And we can write this, basically how what the quantum computer does in a very general way is something like this, right? So basically, just like any computer, if you think about it, what does a computer do? Well, computer just very generally, what it does is that you have some input state, that's in the memory of your computer. I'm just talking about classical computers here, just your everyday computers. So you have some input state, algorithm does something to it, and presumably you want to know what happened, and you want to know the result of it, right? So if you think about any program, actually that's what it really does. If you're doing an Instagram filter, you put your photo in, that's your input data, and then Instagram puts a filter on it, changes the color a little bit, that's your output. So that's a simple example, but I mean, basically anything is ultimately like that, because it's just about you have some input to it, and then eventually it uses that in order to make the final thing that you want. So if it's Microsoft Word, eventually what you want is the beautifully laid out piece of document, and so that's the output, and then the input are all the keystrokes that you do to create the document, and so forth, right? So quantum computer is basically the same. You have some kind of input state, but then this time it's not just like a classical data, but it could be this more general quantum state, and so that's your input to the quantum computer. Quantum computer does some kind of processing. That's basically the algorithm part of it. So this is some kind of algorithm which transforms the input state into the thing that you ultimately want. And then here's the output. And then another thing that we don't really think about so much in classical computing, because it's obvious that you can read it out. In quantum mechanics, it's slightly less obvious that you can read out this information, because measurement is actually a sort of a destructive process, right? It actually can, well, it's random, as you know, and also it can sort of change the state that you just had. So generally speaking, you've got your state, you put it in your measurement device, and then you'll randomly get something out here. So I guess the new part of the quantum computer is the fact that, okay, so firstly, these states are these quantum states, not just 0, 1 something, but it could be the superposition. The algorithm itself is some quantum process, and it's generally this kind of unitary rotation. And then finally, there's measurement that you have to deal with. And then, this whole process eventually has to produce something kind of useful to you at the end of it. And then, so this is the thing that you read out, actually. I mean, if you could get this, actually life would be much easier, but actually, you can't personally read it out unless you measure it, right? So basically, this is the thing that you actually get. And so somehow from this input state, you need to get something useful here. And so essentially, this is the goal of a lot of quantum research at this point, still now, is to design quantum algorithms. How do you design some kind of algorithm that is basically going to do something interesting to you, and you get something that you want out here. Okay. Hope that makes sense. Let me continue, unless there's any questions. No. Okay. Okay. So let's talk a little bit about these steps that are involved, and I guess the most interesting one here is this algorithm part, right? Because that's the thing that's actually, I guess, going to do your calculation, right? So this, what is this, algorithm part of it? So as we kind of learned already, basically any kind of change in the state is governed eventually by Schrodinger's equation. Schrodinger's equation changes the state from some initial state, time equals 0, to some other final state. So basically, if you're talking about a change of state, then basically we're talking about a Schrodinger evolution. So basically, we're talking about Schrodinger's equation in a general sense. And so that basically means, as we learned in the last slide set, that we are dealing with a unitary process. So quantum states evolve according to a unitary evolution. So basically the way that you can think of this is that we've got, an initial state, say it's made up of this n qubits. So the dimension of this vector is 2 to the power of n. And then you're going to apply some kind of unitary. Okay, so some unitary matrix. And this is the output of the quantum computer. And then maybe you're going to go and measure this, but that's another step ahead. So let's just talk about this algorithm part. So you can probably imagine that, this is still very general. So, this input state can be anything, but actually also this unitary also could be anything. Think of all the possible matrices that you can make that are like 2 to the power of n times 2 to the power of n. Okay, so it needs to be a unitary matrix. So that makes a little bit of a restriction on the type of matrix it is, but still there's a hell of a lot of different matrices that you can make, actually. And so this seems a little bit almost too general. Like, how do you even start thinking about all the possible, unitary matrices that could potentially be an algorithm? So the way, I guess, we deal with this as sort of humans is to not really think of this like in this term, which is certainly mathematically correct, but it's just too much of a mouthful to really kind of understand this. So as humans, when we think about how do you write code, well, you don't just like start writing code by thinking of this kind of input-output relation, right? Like, so just to go back to the Instagram filter, it's not like you think of every possible picture that can ever be inputted into the program, and then you think of all the possible pictures that can be made. This is sort of almost this kind of thinking. What you actually do is you break the problem down into pieces, right? And then so you sort of say, okay, there's a step 1, and then there's step 2, step 3, step 4, and then so we do this, and then we do that, we do this, we do that, we do that, and then we get the final thing, right? So there's a kind of a process to it, rather than just trying to do it all in like one hit. Yeah. So basically, what we do generally in when you write code is to sort of break it into a sequence. And this is where we sort of have the idea of these kind of elementary gates, right? So, I mean, this is not really, it's not like coding, it's actually like a step before coding, right? So, you're probably all familiar with writing code like, you know, a for loop and, you know, if this, you know, do this, and then if that, do something else, and, you know, that kind of coding. You know, this is a little bit more basic than that. This is at the level before that, where we're just dealing with pure logic gates. Okay, so how many of you guys are sort of familiar with you know, just these gates, like these logic gates, like these and, or, not, and NAND, and these types of gates? Are you guys all familiar with these types of gates, like and, or, not?
I only know and or.
Okay, all right. Okay. What about the rest of you guys?
You mean like what?
Sorry, my volume's a bit low. Let me try and turn it up. Sorry, what was that?
I mean like what are the gates like?
You know, like these logical gates, these Boolean logic, like and, or, not, and this kind of stuff.
Like this kind of thing, like this and this.
Yeah, that, yes. So you encountered
yeah, and also the triangle.
Triangle. Okay, I don't know. I'm not quite sure with that particular notation, but what does the triangle mean?
Complementary. I think the complementary. Oh, is that the complementary? I kind of forgot, but like, yeah.
Okay, all right. Well, anyway, I think you guys have maybe seen it in bits and pieces, but okay. Well,
yeah, I think maybe in Python there's the Boolean types of kind
okay.
of algorithm.
Right.
Yeah.
Okay, good. All right. Okay, so it sounds like you've sort of seen it, maybe not like studied it exactly as such, but you've seen it here and there. Okay, so let me go back. So I have to start this again. Oops. Okay, so yeah, so basically, yeah, there's this kind of you know, way of dealing with Boolean logic, which is, you know, if your variables only are 0 and 1, right? And so when you are talking about like digital logic, you know, the most fundamental step, of course, so in a computer, you know, you guys, you know that in a memory of a computer, ultimately it's all zeros and ones. But actually rarely we don't really deal with zeros and ones, right? Like when we write code, it's not like we're typing zeros and ones. Of course, we're, you know, typing more sort of high level code, but, you know, that high level code is actually ultimately, you know, decoded into this kind of Boolean logic, because ultimately the computer has to be able to perform, you know, manipulations of zeros and ones, right? And so, you know, that extremely basic level of logic coding still, but it's, you know, kind of the most basic level. You're dealing with this kind of Boolean logic. And so in Boolean logic, basically you have these types of particular gates where you have like, you know, each of these lines here will be a variable like 0 or 1, and, you know, you have different types of gates here which are like and, or, not, and they manipulate this you know, information in certain ways. Okay, so in classical digital logic, there's a famous result that says that that you can actually make any basically any kind of digital logic circuit purely out of NAND gates. Have you guys heard of that?
No, and what is actually a gate?
Okay, what is a gate? Okay, all right. Well, we'll okay, we'll do that. Okay, fine. Well, okay, so what is a gate? All right. So so how does this something like this work here? Something like this work. So okay, do I have something on the next page? Okay, well, I can just explain it here. Okay, so What is this thing? Well, how about we just start with something a little bit simpler, which is, well, let's have a look at this OR gate here. Okay, so this OR gate, which is this thing. So basically, what this symbol here means that as the input, so the input is always to the left, and then the output is to the right. Okay, so basically, you can think of, you've got your information coming in, and each of these lines here can be basically 0 or 1. So you can think of basically time is going sort of this way. So there's a sequence that's being executed, and in the memory of your computer, basically there's different bits in your computer, and they can be either 0 or 1. So each one of these lines can be 0 or 1. Okay. So basically what this gate does is to take 0 or 1 as the input, and then it will produce a particular output according to a particular rule. Okay. And so the rule for OR, the OR gate rule is that, so if we go the input, well, maybe we can follow the notation on the right there. So A is the first input, B is the second input. Oops. Okay, and then the output, so this everything is binary. So there's basically 4 combinations of inputs here. And so A can be 0, A can be 1, B can be 0, B can be 1. So ultimately there's 4 different input combinations. And basically the rule for OR is that, and we can think of 0 as being false, and then 1 as being true. Okay. So if, and OR is sort of like, the meaning of OR is that it's like either this one or that one, right? So, so basically it follows more or less the logic of the word OR. So if basically both are false, then the whole thing is false. If one of them is true, then the output is true. So that one is true as well. Now, if both are true, then for OR, it's actually also true. So basically what happens here is that you have a bit that is, well, 2 bits that are going in. We're just talking about classical stuff here. So 0s and 1s. And then the OR kind of processes these 2 bits and then just follows the rule according to this, it's called the truth table, and outputs the, a single bit over here, and that will be 0 or 1 depending upon, this truth table that I've got here. So that was the rule for OR. Now the truth table for AND is something like more like this. So for AND, it would be, so if it was A and then B. So again, we've got 2 inputs like this. Okay, and then the output. So the meaning of the word AND is sort of like, something is going to be true if like both conditions are satisfied, right? So the output for this one is 0, 0, 0, 1. So there's a slightly different truth table for this one. So that's AND. Yeah, so I mean, just to, I guess, give an example. For example, I could say, okay, I'm going to go to the beach only if it's Wednesday and it's sunny. Okay, so basically, both of those conditionals have to be satisfied in order for you to go to the beach, because you're only free on Wednesday, and also you don't want to go to the beach if it's raining. So you only go if it's sunny, right? So there's a kind of a logic that follows the word and, right? Now, what's NAND? Well, NAND is actually just, it's like a combined gate between the NOT gate, which is this one, and the truth table for the NOT gate is something like, this is a one input gate. So in this case, the input is either 0 or 1, and then the output, it just flips the result. So this is 1, this is 0. Yeah. So if you input 0, it'll output 1. If you output 1, it'll be 0. And a NAND gate is just a combination of a NOT gate and an AND gate. So this thing here, this gate here, basically it's actually the same as, so the symbol for the AND gate, I think normally looks like this. And then the symbol for the NOT gate, I think it's like this little circle. So basically NAND is just the opposite of AND. And so if you can see that if you flip the output here, so if you just flip this one to 1 and all these to 0, then you'll get exactly the truth table that I've written there. Okay. Is that clear?
Yes.
Okay. All right. That's good. Can't see the rest of you guys, but I hope that's clear. All right. Okay, that's good. Sure. Okay, so wrong slide.
So or also nor also means or and not.
That's right. Yes, exactly. Yes. So that there's a thing called a NOR gate, which is an OR gate and then a NOT at the end. Yeah, exactly. Yes. So, okay, well, if you haven't done this before, then maybe you haven't heard of this result, but basically there's a famous result that says, well, you can make any algorithm, which basically means if you think of all the possible algorithms that you could make with the combination of these types of gates. So here's sort of an example here where there's some kind of combination of these gates. Okay, and ultimately when you write code, eventually it gets boiled down to something like this, right? So it's just like a sequence of applying these ands and nots and OR gates and things like this, and basically all these things, just gets applied in sequence. Now, if you think of, all right, so what are all the possible kind of algorithms, meaning these types of digital logic gates that you can possibly make. Now, obviously, there'll be a huge number of combination of these gates, and so you might think, okay, so what kind of gates do I need if I wanted to make an arbitrary logic sequence, which eventually corresponds to some kind of algorithm? Because we want to be able to write any arbitrary algorithm that you might want to do, right? So what is the most essential kind of set of gates that we kind of need? Do we need an and an or and a not, or do we need just an and an or something like this? And basically what people worked out, and I'm not really going to show you, but there's a famous result that says that actually the only gate that you actually need is this so-called NAND gate. Okay, so this one. So if you can just do this one, actually you can make everything else in terms of combinations of this particular gate, right? And just so that you can see why this might be, it's basically because this NAND gate, if you do a couple of like little tricks to it, you can actually make all these other gates, like say a NOT gate, if you combine the inputs of these ones. And basically what this one means is that you just double up the input of the of the inputs here. So basically when you have like something like this, it just means that both of the outputs are going to be the same. Okay, so you can see here that if you have an input 0 here, then okay, you just double up the input. So basically, it's this line, and then you have the output of 1, and then, or if this was 1, then you double up the inputs, and then again you have the output. In this case, the output is 0, and you can see exactly that's exactly what not does. Right? You can also make an OR gate like this. I'm not going to go through the working, but somehow you can construct an OR gate. It's pretty obvious you can make a AND gate as well, because if you've got you can make a NAND gate like this, and a NAND is a knot of an AND, so not like 2 knots in a row just actually gets you back the original thing. So this is actually the same thing as a regular AND gate. Okay, so you can see that already that the NAND gate can make a NOT gate, it can make an OR gate, it can make an AND gate, and I think it can make basically any types of gate. And then so if it can make any of those types of gates, then you can start to combine them in various orders. And basically the only gate that you actually need to do an arbitrary digital logic circuit, which eventually means an arbitrary algorithm, is this one gate, which is the NAND gate. So it's kind of an interesting result. That clear?
Sorry, what is the little box in the picture of the NOT gate?
This one?
Right. Yeah.
What is that box? Right. It's not a box actually. It means more like you have your logic memory element, and then you just split it into 2. Okay. So if this is 0, then this would be like 0 and 0 like this. And if this is 1, it just like splits it into 1. Because this is classical logic, it's not quantum mechanics or anything. You can just like copy the bit, and you just have 2 of them. Okay, so it's not a box there. And then basically those like duplicated bits just goes into the NAND gate, which is got like 2 inputs here. So this, it's not really a box. It's just like this is the NAND gate, and this is just the doubling up thing. So it's just like splits it into 2 and just copies it. It has like, now you got like two bits which are the same. Does that make sense?
Yeah, I get it.
Okay, good. Okay, anyway, this is not really central to the whole quantum thing anyway, but I mean, what I just kind of wanted, for those of you who are familiar with digital logic, then this might mean a little bit more, but basically, I think it's still useful to kind of know this, because like a lot of quantum computing is sort of working at this kind of similar level to this digital logic. Okay, so in fact, when we look at quantum circuits and quantum algorithms, the way we write it kind of looks a lot like this. We'll have a notation where time goes from left to right, and then executes a sort of a sequence of gates. But basically, these things are a little bit different, but the overall thinking is a little bit similar. Okay, so now, so what about the quantum case? So in classical computing, we know that NAND gate can make an arbitrary algorithm eventually, and we want to do something similar in the quantum case. So what is the most basic gate that you actually need in quantum computing? Maybe if you could just do all of quantum computing just with like one gate, that would actually simplify things a lot in a way. in terms of like the guy that needs to make the quantum computer, because he just has to focus sort of all his attention on just making that one quantum gate, and then that's it, right? So it's seems like a much more easier task to sort of to do, rather than to sort of kind of be faced with this completely general kind of unitary matrix, right? So by making this kind of gate decomposition, it sort of simplifies the algorithm construction process. So I'm not really going to show you why, but basically there's a very similar result in quantum computing, and this basically says that you can actually make an arbitrary unitary matrix or algorithm just from 1 and 2 qubit gates. Okay, so it's a little bit more complicated than the classical case, and I guess it should be, because quantum states are sort of generalizations of the classical case. So we need gates which are a little bit more complicated, but still we can make a completely arbitrary quantum algorithm just from 1 and 2 qubit gates. Okay, so let's sort of explore this idea. So let's look at sort of one bit gates first. Okay, so let's actually kind of think of what a gate would be in the context of quantum mechanics. So I could just go and tell you just now like what some gates are, but I just want to sort of give you a little bit of a thinking process, maybe just so that you know kind of where this comes from, and just how you might sort of derive such such gates, if you like. So let's go back to the classical case just for a minute, and let's think of what types of gates are possible in the case of just like 1 bit. Okay, so we just got like 1 bit, and in fact for this kind of classical case, there are only actually 4 possible 1 bit gates that you can possibly make, because things are very simple in the Boolean world, digital 0-1 world, because basically there's only 2 numbers, 0 and 1, and so even if you think of all the possible functions, there are not many functions, right? I mean, when we're thinking of continuous numbers, there's infinite number of functions, because basically there's infinite numbers of numbers, right? But in the Boolean world, there's not so many numbers, and so also there's not many functions. Okay, so I mean, one way to think of this is to if you just plot functions. So if you just plot, so here's your input numbers. So there's only 2 input numbers, right? There's 0 and 1, okay? And there's only 2 output numbers, okay? So there's also 0 and 1, okay? So there's only sort of 4 points here, basically. So here, 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 and here, okay? And so actually, we can write all the possible functions just already on this one graph. So this is one function. This is the function. If you were to write this as an equation, you would write this as basically fx is equal to x. Okay. Here's another function. It's the function like 1 minus x. It has a negative slope. It's has an output of 1 when input is 0, output of 0 when input is 1. There's 2 more functions. This one, which basically gives 0 all the time, and there's another function which just gives 1 all the time. And those are all the possible functions that you can have for Boolean logic. There's only 4 functions in the whole thing. Okay, and we can write the sort of the digital logic versions of these. So this one that says f of x is x. Well, this is actually the thing that, you input 0 and then it outputs 0. If you input 1, it outputs 1. So basically, this is actually, logically speaking, doing nothing, right? So this is this one. The symbol for that would be just a wire, because it just does nothing. It just keeps the information and then just transfers it to the next stage. And the truth table is like this because this is just the input and that's the output. Okay, so that's the first function. The next one, which is over here, oops, yep, this is 1 minus x. This is what we would call the not. I should label this 2, because basically this flips the input. So if the input is 0, then the output is 1, and if the input is 1, the output is 0. So it just flips the input, changes to the opposite value, and the symbol for this would be the NOT gate, this one. There are, I guess, 2 more, and this one doesn't really have a very good symbol to it, so I sort of just made it up. But this case where the output is always just 0, so I'm going to call this gate something like this. So it's the reset to 0 gate, because basically no matter what, the output is 0. Okay, so the output is 0 no matter what. Doesn't matter what the input is, in fact. And the last one is just this one where output is always 1, and so this is like reset to 1. Okay, so classically, those are all the possible gates, all the possible, or functions, if you like, that you can possibly have in this case. So now let's look at what happens in the quantum case. Oops, there. Okay. Okay. Just erase that. Okay. So now let's think what happens in the quantum case. Well, let's try to make the quantum versions of these, because basically what is different in the quantum case is that the input is not just 0s and 1s. We can have actually an arbitrary state here. So instead of having just 0 and 1 as the input here, as the input, we can have a state like alpha 0 and beta 1, right? Okay, because in quantum mechanics you can have a arbitrary superposition. You don't have to just have 0 and 1. You can have linear combination of 0 and 1. So we can make a analogous gate to the wire gate, because we know how to do that. Basically, if you have a matrix that looks like this, which is the identity matrix, then this is exactly what it does. So we can actually sort of generalize this kind of digital Boolean logic case to this quantum case just in this way. So we can make the quantum version of the wire, which is just something that just does nothing. It just transfers the input state to the final state without altering it. And we can say that our gate, in this case, it's not much of a gate. It's actually just does nothing, but it's still a kind of a gate, I suppose. The unitary matrix corresponding to this is I, the identity. Okay, and this is a unitary matrix, because the unitary matrix is defined as something like this. Okay, and if you think about what's the inverse matrix of the identity, so the inverse matrix is something that has, when you multiply it with the inverse, then it should give identity, right? So what we need is identity, and then matrix multiplication by something is equal to identity. So obviously the inverse of the identity is actually also the identity. So so we know that the inverse of the identity is just the identity. Now the transpose of the identity matrix, or conjugate transpose. So so what we know here is that the inverse of the matrix is I. Now, what is the conjugate transpose? Well, if you take conjugate transpose of this, it's also I, so they're the same matrix. So yes, it's unitary. So it's definitely something that you can do with Schrodinger's equation, because Schrodinger's equation, it's unitary. So we should be able to do it. And so basically that's a successful generalization of the classical case. Okay. So now let's try and look at the NOT gate. Okay. So the NOT gate, what it does is, in the classical case, what it does is that it takes 0, outputs 1, takes 1, outputs 0. Okay. So what we're kind of looking for is something that does the same thing. And well, if the input state here is some superposition, so maybe we can write it as a vector this time, alpha beta, then if you think about what this X matrix, so we've encountered this X matrix before, then basically this is exactly what the NOT gate also does, because basically, obviously if you multiply by this matrix, it will flip the output from 0 to 1 or 1 to 0. And this thing is, so if you multiply the X matrix by this arbitrary state, then it will basically reverse the orderings of the two states, right? So alpha beta becomes beta alpha. And this is also a unitary matrix, because we know that actually X times X is equal to identity. We did that like a slide set ago, or you can just try it now. So basically the inverse of the gate is actually X. And then the transpose conjugate of X, so you can just take the transpose of this, is also X. So this is also unitary. So so this is basically another good generalization of the classical case. So basically here we've got like two kind of generalizations to the quantum case of the classical gates. Okay. But actually for the other two gates, we're actually going to run into problems. And so for example, the closest that you can do to like a reset to 0 gate might be like a matrix that looks like this, okay? Because you have some initial state, and then in order to always have only the 0 state on the output, right? You kind of need to have this as 0, right? And in order to have that as 0, then these matrix elements have to be 0. And then, well, you don't have to put 1 here necessarily, but let's try putting that. Then this is the output state that you have, right? Okay, so it's going to be alpha plus beta. So maybe can you guys sort of spot or see why this would not be a valid quantum gate?
Because the inverse, well, wait a second.
No, I think you got the right idea already. Yes, it's the inverse. Yes.
It's not invertible.
Yes, exactly. Yes.
Yeah, not invertible.
Yes, it's just not invertible. Like, so remember when you have this, like the quantum state should always be normalized, right? And so let's just look at an example. Like, suppose alpha equals 1/√2, which equals beta, right? Okay, then basically in that case, this thing would be equal to √2, 0, right? So firstly, that's not normalized. And then so you might think, oh, okay, now I need to normalize it. But actually, it's not really consistent with a unitary matrix, because unitary matrix should always preserve the normalization. It's actually one of the properties of unitary matrices. It preserves normalization, and this doesn't. Okay, so this is this matrix here is sort of a bit, you know, it's problematic in that way. And yes, and exactly as you guys just said, now, you know, if you think about it, like, you know, if you ended up with this state √2, 0, you know, you couldn't invert that to always go back here. There would be many states actually potentially that could give this final state, because yeah, if it always resets to 0, then how do you know what it originally was? Because if it's, you know, you start with any state, it goes to 0, the 0 state, then you know, there's no trace of the information that it originally was. And so how do you get back there? Maybe yet another way to think about why this is not a valid matrix is to simply try to calculate the inverse matrix. Yeah, so, you know, if you try to calculate the inverse matrix of U, then I think you're going to run into problems, because this will have, I think, singular eigenvalues. And so, you know, if it's got 0 eigenvalues, then I think you know, cannot find a valuable a valid inverse. So you can certainly calculate the matrix transpose. This would simply be 1, 1, 0, 0, but you can see that that is definitely not the inverse, because if you try to calculate this thing 1, 1, 0, 0, you're not going to end up with the identity. Let's see what you end up with. Get 1, 1, 1, 1. Okay, so this was supposed to be the identity, but it's not the identity, right? So yeah, basically it just fails a lot of checks. Perhaps this one, just evaluating this thing, could be maybe the simplest just way to check whether it's a valid gate or not. So if you evaluate this thing and it's not the identity, then you can immediately tell that it's actually not a valid unitary, and hence it's not a valid well, quantum gate. Okay. Right. Okay. And then the story for this last one is the same. Oops. Where am I? Yeah. Sorry for this last one is the same. You know, reset to 1 is obviously not invertible either. Okay. So I think I already said the answer for these, but yeah, they're basically not reversible. So unitary gate cannot be made for these guys. Number 3 and 4. Okay. All right. So, you know, we kind of tried to generalize the classical case and ended up with, well, 2 out of 4 of them were valid kind of quantum gates, which is kind of encouraging, I guess. Like, it's sort of means that you can make some quantum gates. Now, are there other quantum gates? Well, the answer is yes. There are actually many 1-qubit gates. And so here are just a couple more examples. So for example, here, what we've been talking about, this Z, we've been talking about these X, Y, and Z matrices a lot. So this Z matrix is another one. Actually, Y is as well. It's just not as commonly used, but also that's another one. But Z is another valid gate. The action of this thing is basically to change the sign of this term here. So this, if you put in alpha and beta, then the output is alpha and minus beta. And you can tell that this is still normalized, because if you just do the normalization of this one, then these minus signs cancel, and basically you still have a normalized state. Now mathematically you can tell that this is normalized, and the easiest test for this is to again evaluate U dagger U, and you can always find U dagger pretty easily. It's just transpose conjugate, and then just do matrix multiplication. So this is a very quick test to see whether you've got a valid unitary. And so, if you just calculate Z dagger, it's actually the same as Z, and then Z squared is equal to I, as we sort of encountered before. Another very famous gate is this so-called Hadamard Gate. Now, presumably it's named after Mr. Hadamard, but actually I don't really know who this guy actually is, I must admit. Perhaps he was more coming from another field or mathematics or something like this. I'm not quite sure, but anyway, it's named after him. And basically this is another type of gate that satisfies this relation, and it has this definition where it's like ones everywhere except for this -1 here. And you can tell that it is unitary because if you take the complex conjugate transpose, actually it's the same matrix. But if you do the square of H, then you'll find that actually this will be identity. And it works out like that basically because the when you do this matrix multiplication, 1, 1 minus 1, say if you look at this column and this row, this is orthogonal, okay? So this is going to be 0. And then this combination of this one and this one will also be 0. So all the off diagonals are zeros, and if you have the proper normalization, it'll be 1. So the reason why this is a very famous gate and very useful is because what it does is that if you start in the state 1, 0, so this is like the state, if you write it in the bracket notation, it's just like 0. So, if you just start in the state 0, you apply this gate, what it does is to make like this superposition state. And I think I said earlier on, like maybe in the first day of the course even, maybe that, part of the power of quantum computing is, being able to use this superposition. And the superposition state is, kind of what you want to exploit in quantum computers, because this is what gives you that sort of parallel processing power. And so, this gate is a thing that makes this superposition state. And this is why a lot of quantum algorithms involve this thing. Okay. Okay. Right. And then again, those are just like 4 particular gates. They are pretty common kind of gates, and people do use them in quantum algorithms. But actually, there's still more gates, in fact. And in fact, this is the most general 1-qubit gate that you can write. And what this is, so here you've got this X, Y, and Z. These are these so-called Pauli gates that we've already encountered before. And this NX, NY, and Z, this is some unit vector. It's a vector that just has length 1. And these are just real numbers, okay? So there's no complex numbers here. So maybe I should have written this here. So these are real. Okay. But it's a unit vector because it's the modulus squared adds to 1. And it's a matrix exponentiation of this thing. And this is some angle phi divided by 2. And there's a complex I here. So the matrix, so basically what this is maybe, I should write this as some unitary. It's the matrix exponential of this sum of Pauli matrices. And, there's some factor here. And we can tell that it's actually unitary because we can just do a quick calculation. So to find the U dagger of this, basically what we have to do is we basically just have to take the dagger of everything that's inside this exponential. So nx plus ny plus nz z. Now, if you're thinking, oh, but why is it like the dagger of the exponent? Well, again, it's because, if you have a matrix like this, right, you can always expand it in terms of the power series like this, a squared on 2 ... And then if you want to take the dagger of this thing, then it's basically taking the dagger of all that. And then the dagger is actually a distributive thing. So it's actually I dagger, then plus a dagger plus a squared dagger over 2 ... And then because this is the same matrix, it's actually the same thing as I dagger plus a dagger plus a dagger squared 2. So basically just it's this is actually the same as a dagger. So you can just take the exponent, the dagger and the exponent, and it's the same thing. Okay. Now, taking the dagger of the exponent is a bit easier because sorry, it's a bit messy, but the only thing that actually changes here is actually this I here. So the only thing that happens is that this I changes sign. This phi is, again, it's a real number, so the dagger does nothing. This nx is a real number, does nothing. And actually x dagger is the same as x. Y dagger is the same as y. And then z dagger is the same as z. Okay, so actually, the x, nothing happens to it. So nothing happens to basically all these things, all these terms inside the exponent, except for that I at the beginning. And if you do a matrix multiplication of U dagger and then U, basically what you have is a multiplication of, this thing with the plus I and all this stuff, and a multiplication of this thing with the minus I of all those things, and then they cancel, and then basically you'll get just e to the 0, and then that's I. So this is a unitary matrix, and basically maybe we can sort of finish up here for today, but this eventually has the interpretation of actually a rotation around a particular axis in the Bloch sphere. So you can take a state on the Bloch sphere. There's some axis here that you're rotating around. This is what this this vector actually specifies. It's the direction of this axis. And then the angle that you rotate it by is this angle phi here. So if you've got some original state here, it will rotate it around some angle, and it will end up at some point, different spot on the Bloch sphere. Okay, and that's actually the most general 1-qubit gate that you can write. Maybe we'll leave it there. Any questions?
Like sometimes if we want to express the state in the Bloch sphere, like sometimes I think, do we need to take out the global phase? Because I think like the cosine theta over 2, like, and theta can only take 0 to pi, like it only it only is a real number, and it's can only take positive number. So for some states, like we sort of need to take out the global state, right? Global phase.
So I'm not quite sure which cosine you're referring to. So are you talking about like just in the general, when you write the Bloch sphere, sorry, in the Bloch sphere representation? Oh, sorry, no, oops, my mistake. So sine of phi over 2, and then e to the I phi of 1, right? So this is like the general 1-qubit state, right? And then are you talking about the cosine here, or?
Yeah. I mean, yeah. If this take this, like it sort of only applies to this form.
I would say that the global phase, like maybe the way that I would think of it is that it's the Bloch sphere representation is like plotting the set of 3 expectation values like this, right? So if you have the state and then you evaluate expectation value of x, y, and z, and then you have this like three coordinates, right? And then you just plot that in terms of like this unit sphere, right? I think that's how you go from the state to the Bloch sphere. And if you calculate expectation values, the global phase should never matter, because when you calculate the expectation values, the effect of the global phase just cancels out completely. So like if you try to match it to this definition, then yes, I mean, maybe you need to get rid of the global phase to match it to this one. But then if you do it the method, like you match it to the expectation values, then I think you should never have to really even think about the global phase.
Okay, I'll try that.
Okay. Okay. All right. Then maybe we'll leave it there. And I'll see you guys next lecture. Okay.
See you.
Bye.